Hello, viewers. Welcome to the semiconductor webinar. Today we have the second episode, and today we have our guest Bhavesh and Jayshree. We
Hello.
are excited to, yes, we are excited to two promising young minds. Bhavesh is currently pursuing the his M.Tech at Nirma University and pursuing internship at Monk 9 Technology. From tinkering with Arduino boards to exploring semiconductor fabrication, his journey reflects a strong passion for semiconductors in India's chip ecosystem. Another guest, Jayshree, is also an MTech student at Nirma University, bring a unique blend of experience from verification domain and growing expertise in fabrication. With hands-on clean room training and strong academic industry collab experience, her journey reflects a strong passion for semiconductors in India chip ecosystem. Together, they are on a mission today to contribute meaningfully to India's semiconductor growth through this webinar. So, over to you, Bhavesh and Jayshree. Yeah, go ahead
Well,
and
so basically, I would like to add some viewpoints. Well, I have done many projects on Arduino, Raspberry Pi, DSP, uh, different boards. One thing came across me that how does thing works. Then my sir taught me the VLSI subject, and all through this time, I learned about VLSI. And to get into a proper VLSI domain, I started my uh, core into the VLSI, and I took the admission onto MTech in Nirma University. And then I got like we had a practical thing in a CSIR CD lab where we got gone through fabrication process, a 15-day proper SHIL program, semiconductor high impact learning program, where I learned a proper fabrication from basic, that how a silicon is cleaned till the end, how metallization works, how dicing goes. So that made me curious that not just semi silicon itself, but many materials are there, and different material have different properties. And we heard about uh, we hear new like daily news about different material, gallium arsenide, gallium nitride, in different sectors, defense, automotives. So that made me like I want to get into the fabrication. I want to play with materials. I want to work on different things, quantum, optoelectronics, thermoelectrics. So yeah, that made me inspired, and I wanted to work in it. I'll then Jayshree will continue.
Hello everyone. Myself Adwani Jayshree, and I would like to add I have been to the multiple. I mean, during my college, I was confused between embedded robotics, VLSI domain. Eventually, at that time, semiconductor was not introduced. So yes, I jumped into the first company which was in my hand. That was like a verification domain, and I was working over there, and suddenly I just got to know about semiconductors, and I was during my verification time. I was just curious what the things are made and how are the eventual background things are going on. So while exploring, I just got to know about the semiconductors, and later then I was like going thinking of where to pursue it. Like I wanted to go for the masters. I have searched a lot in India. It was not, I mean, from eventually IITs and some of the colleges are not providing that course. So yes, Nirma was providing this course and we just opted for it. And eventually during the starting I was confused yet what is the semiconductor until I was introduced to the CSIR lab, which is in Pilani. And then the things got up to the clearly what are the semiconductors, how are these chips are fabricated, individual steps from basic to advanced, everything was been cleared for me. And eventually like I'm very sure about it. Like yes, I am very happy to be part of the semiconductor. And no doubt its verification was also a good part. But yes, that's giving me thrilling experience while working with the machineries and handling with the care and multiple sort of the things with the fabrication. So today we are going to just start about like basics of fabrications, like how the things of the fabrication have been initiated, basic flow to everything which we can cover as for now, because semiconductor is a very vast domain. We will try to complete as much as we can. Let's see what comes to the next. Uh,
Okay, we'll just start the presentation.
Yes, go ahead.
Okay, so firstly, what is the fabrication flow? Uh, the fabrication flow, then orientation, then how it's being cleaned up, and oxidation, layer by layer processing of the fabrication, like oxidation, lithography, and much more things. So basically, what is the fabrication flow? As you can see in this image, there are the start process, where is the wafer itself, the whole wafer, which you can consider in your mind, consider as a CD disk. So a CD drive, compact drive. So you can think of it, and then multiple layers have been fabricated, like oxidation, then lithography, then etching, then ion implantation. Everything has been step by step, layering by layering, and we are just making a formation, a device. So eventually, each of the device has been stacked up, and with the help of different processes, individual steps, which we are going to cover in the future further slides. And then the packaging introduces, like from dicing itself, you can see it, from dicing to die etch, then wire bonding, then after wire bonding, that it's like encapsulation to harden the device so that it can get prepared from the environment, to doesn't get interrupted with the environment and stress and everything. Then how to, like, if we are completely sure that how the devices has been created, so we are going for the testing purpose, like if the whole completed device is good or not, it's defect free. There are multiple testing reasons why we are going for the testing purpose. And then the final step is the packaging. After packaging, the product is finished to get into the market. So next for it's wafer orientation. I will handle it with the Bhavesh.
So generally, there are several different types of wafer orientation are there. 10 and 111. These are one of the basic orientation that are in the market. They are mostly used. There are also different 110. Then there are 200 and different. Now, reason of you explain having 100 and 111 as a name, it's because their crystallography. Now, in this all, crystallography plays a major role because we, someone from the science would know easily that the arrangement of atoms are generally in a cubic structure. So they are face centered, simple cubic, body centered, backward centered. So there are different atomic structure that lies, so such that way the wafers are made. And with the changing of the orientation, like 111 is a mechanically very strengthful wafer. So 111 is generally used for the MEMS devices, power electronics devices. 110 is used for better oxidation. If we want to make an IC, 110 can have a better oxidation. Like we, if we want to just do oxidation and make an IC or make a MEMS device or a RF device, 110 is also is a better option. Then 100 orientation, we can make ICs which are based on CMOS, FinFETs, Gale or all around FETs. Now there are different wafer orientation, but these are generally used in the market on silicon. And majorly the crystallography works in here. So that's how these wafers are made. And the cuts which you see, there are primary flat cuts, and then if my mouse is visible, there are primary flat cuts, there are secondary flat cuts. So it also changed the crystallography and also the use of it. Like these are N types and P type. N types for which N type doping, then P type doping. So depends on the requirement. We have a crystallography, wafer oriented structures, and N type and P type. So now we'll go through wafer cleaning and I'll hand it over to the Jayshree.
So basically, what is wafer cleaning and thinning? The word itself term is like what if how to we are supposed to going to clean the wafer, and to thinning means how the wafer like size get decreased. Main thing is that okay. So firstly, we will go for the cleaning. So there are the multiple steps. Eventually, depending upon the industry, we are going to change the requirements basically. So firstly, we will go for the organic cleaning. What is organic cleaning? To basically, we are doing it for removal of the residue like photoresist or oils, like contaminants, our body contaminants. Like our body eventually produce a lot amount of sodium. So how to remove it? So basically, we are going for the organic clinic, then dry clinic, and then again inorganic clinic. So firstly, for the like chemicals which you are using for the organic cleaning is acetone or methanol to remove the solvents. Like in this image, as you can see it, consider the SI surface as a wafer, and then the multiple numbers of contaminants which have been stuck over the wafer. So how we are going to remove it? There is an inorganic material, then organic materials, then other contaminants, particles, multiple numbers of the contaminants have been spread over the wafer. So firstly, we are going to for the organic cleaning. Organic cleaning basically removes with the help of the chemicals like acetone and methanol, and then with the DI water we are going to rinse off the material, I mean wafer surface, to make it hydrophobic. And then eventually in later step we are going to use the N2 gun gas, like hydrogen gun. So hydrogen to blow off the all the water spread over the wafer to make it hydrophobic basically. And then inorganic cleaning. So basically what is inorganic cleaning? So there are the two cleaning, S1 cleaning, S2 SC cleaning 1 and SC 2 cleaning. Okay, so basically it's ammonia and hydrogen peroxide with the DI water. So we are just going to do the first layer of that, and then in the S2, we are going to remove the HCl, hydrochloric acid, and hydrogen peroxide. So in that we are going to remove the second layer, and then the buffer HF. So what is buffer HF? It's kind of buffer HF is purpose is to remove the native oxide layer from the wafer to clean the wafer in a way that it's free for the oxidations layer. And then this H2SO4 and H2O4, it's basically also used for like piranha solution also. And that is like 3 raised to 1. So basically, that's most important step, and it is basically not I mean like no one can try it because it's a harmful chemical and sulfuric acid. So we have to make sure that we are just doing this process in the clean room. Other than this we are not going to do this. And eventually while you're performing this chemical process, there should be someone nearby you, so that if by God's sake if something happens, there is someone to protect or either to communicate with each other. So we will continue with the wafer thinning. Basically, what is wafer thinning and why we are going to do the wafer thinning process? Basically, for the better planarization, power improvement, and the last thing is to meet the thickness. I mean, constant height or there. If someone, if consider it an example, if the company wants 2 mm, so if there is the multiple layer and the wafer gets is to 3 mm, so we are just again going to do this thinning process. We are going to remove the backside of the wafer, not the processed wafer. Backside of the wafer we are just going to remove it with the help of the chemical mechanical polishing process. And this basically is used to remove the the chemical has been used. As you can see, there is a slurry because this process is going to heat up, and we are going to provide the slurry to make the things cooler, and we are just going to remove the uh, backside of the wafer. Next with the oxidation.
Now I'll continue with the oxidation. Generally, oxidation is required for the silicon wafers. Now we need an oxidation layer to make it as an insulator. In my language, I would say it very roughly, a rough idea. Silicon is like a baby. The reason I'm saying it is like a baby, because even if you take a breath near, or even like exhale near the silicon, it would within a second take the contamination and with make become contaminated wafer. So we need a oxidation as an insulation and also passivated layer, passivation layer to protect it. It work as a gate dielectric for the MOSFET and different transistors if we want to fabricate it. As I said, the passivation layer. We need a proper doping because doping is a part of the fabrication. It also uses a isolation for the locos. Locos is generally now not used much, but locos is also a part of it in the industry. Now there are generally two type of oxidation: dry oxidation and wet oxidation. To give a general idea of a dry oxidation is generally uh, one of the purest form of oxidation layer to be formed on silicon. It is like its end atoms are like bonded like this. If we have a bonding like this, there are no point defects could be there. So there are generally no space like grain boundary would be left, so it would not be contaminated or any sort of like contamination won't happen in the dry oxidation. Whereas wet oxidation, it is very porous. It is like during doing the wet oxidation, it's generally the bonds are like this, so you can see the space between my hands. Within those space during that like we make a connection, between that space there might come a different molecule or atom and make a interstitial defect in it and may cause a problem in the SiO2 layer. So we are generally, if we want to do an oxidation with a during a research, so we would do just a dry oxidation. But we, if we want to run an industry, like generally if someone wants to get into the industry, they would do the industry first way they will do the dry oxidation, then they will do wet oxidation, and again they will do dry oxidation, because it will cover the layer and make a proper formation that the, for porous layer, like as I said, wet oxidation, a porous layer. So with that porous layer, we cannot do the lithography, the next step. So we need to have a dry oxidation on it. So that's why both the type of oxidations are very important to have a mass production also, and for the research also. And then we generated during the thermal oxidation. Basically, for doing an oxidation, we need to go up to 1200 degrees Celsius. There is a thermal furnace or proper furnace is given for that. There are few charges that comes in for fixed oxide charges, mobile ionic charges. This cause a proper like a charges forms a contamination if we don't do the oxidation properly. So these are different charges that can cause a problematic thing for the IC fabrication. Now there are, I have three figures over here: color chart, oxidation furnace, and furnace. Now I'll start with the furnace. Furnace is generally, the oxidation furnace looks like this. In an oxidation furnace and diffusion furnace are almost similar, but we need to change the bubbler thing. If you see the second figure, oxidation furnace, there is a, on the very bottom there is a bubbler and heater. We just need to change the material inside it and we can do the diffusion. But oxidation, for we need a different material for a different processes, because oxidation we need an oxide. So from here H2O would be heated up, and then from the vents it would go to the chamber. If we want a dry oxidation, so just O2 will be passed from, if you see the on the left side, O2 will be passed. If we want a wet oxidation, the HO2 will be vaporized and then will go to the vents. So depending on the oxidation layer, we want wet or dry, we have a setup like that. And then we come to the color chart. Generally, to know how much thickness or how much thin film of an oxide we created, either for characterization we do ellipsometry, or just to get a rough idea, if we don't have an ellipsometry machine, we just to get a rough idea, we'll go through color chart. If we have a, like as she said, she have a CD. If I do the oxide layer, there the oxide layer will form some kind of thin film, and it would change the color of the upper layer. And based on comparing the color, you would know the how much length of the oxide layer. It would approximate length, approximately you would know that this could be the approximately length of the oxidation, that how much of the thin film you have grown in it. And this was a rough idea of the oxidation. You would as you soon as get in the industry, you would know what is ellipsometry and how the color chart is also used. Now we'll go to the lithography. Lithography is one of the most important process in the fabrication. I'll just give you, for those who don't understand the word lithography, I'll just give you the best example. Everyone knows, everyone who have seen Ramayana and just heard about it. We know that Hanumanji and Ramji have written the Ram name on the stone. So the Ram name, that process is called lithography. Like to printing something or to scraping something on some layer or some kind of object. Now lithography here, we want to make a pattern on a silicon wafer. Just to, this is a best example you could understand the lithography, or it is basically patterning on a silicon wafer using light mask and photoresist. Now basic photoresist coating, we need to coat a photoresist with some sort of polymer and oxide or some kind of aerosol material which is to be light sensitive. Like if I generally, if someone have gone through, if you google it on that lithography lab, so you will see a lab with only a yellow light, because the photolithography, just those chemicals are very are not are not be exposed to the yellow lights. So you will see the yellow labs over there on the google. So that's why those chemicals are such that used for the photolithography, because they are light sensitive. Then soft bake. Soft bake is basically the amount of that layer which you coat on it. You have to bake it such that it could make a layer and harden on it. And then we have to alignment, mask alignment. That there is a mask. Mask is such that I'll show you the mask. Mask is, there are positive mask and negative mask. Now, in positive mask, where I expose the light, it would make a certain figure out of it, like how the mask is. And for the negative light, it would harden that side of the part and it would remove other parts. So based on that, there are two types of mask, positive mask. I will explain it right now. And then we have to do the development. There is another layer of the development we have to make sure the exposed layer which is have to be washed away, and then the hard bake for another time. Once again we have to bake that layer at some 120 degrees Celsius for 45 minutes, and we'll get a proper layer of the lithography. Now as I said, there are two types of mask: negative resist and positive resist. Generally mask is made up of, most of the time they are made up of chromium material. So based on some companies also use stainless steel, but it depends. Now importance, as I said, the different determines the feature size, because I have to make a layer, I have to make a different lithography layers on it, use repeatedly. Because of course, if those who are working in a VLSI domain, they are using while doing cadence virtues or any sort of uh, like joining those lines where to complete DRC and LVS. So DRC, they use metal layers, polysilicon layers. So we have to do different type, multiple metal layers. So for that we have to use the lithography. Like we have to continuously do the lithography or have a multiple layers to make a proper form of IC. If we have to make fabricate an IC, so we have to do the lithography multiple times. It we heard of a advanced node, 2 nanometer, 3 nanometer, 4 nanometer. So it is all because of lithography. We cannot do the we cannot go through advanced nodes if we don't add lithography. There is a, everyone knows the ASML. The only, if there would be no ASML in India or in world, there I'll surely say, like the semiconductor wouldn't be this much possible till now. And as I said, as I explained, positive photoresist and negative photoresist, and there is this optical lithography. Optical lithography uses for the like optical like lenses are used to form some sort of pattern on the wafer. And now we'll come to yeah, this is also like proper process. We have to cover with photoresist, place a mask, expose to the UV light with the optical lithography machine, again do the developer machine, then again we have to expose with the positive or unexposed with the negative mask resist, then cut away the unprotected material, and then we have remained. So we have made a proper layer of a lithography, whether it could be metal, polysilicon, polysilicon, whichever we want. Now we'll come to the etching. I'll hand it over to the Jayshree.
So, as we got to know what is lithography, so in lithography, we are creating the steps over the wafer to create a structure. So, what is etching doing? The word itself term is like to remove the selected materials. So, to even create the patterns, there are the two types of the etching process. That is like a wet etching also, and then the dry etching. Depending upon the condition we are required, we are going to do that. Basically, what is the reason we are going to perform the in etching process? So like to create the connections, basically in a normal term, simple term, we can term it as a connections. Like if we are going to connect a power or like power wafer into the different connections, like from bond, I mean from bottom layer to the upper layer, everything is like interconnected. And the interconnects, which are the basically we are just creating the gates vias in interconnects, and eventually more over it. So the flow of it, like firstly we are going to remove the pattern defined by the photoresist, like the photoresist which we have been developed over the lithography. Then the reactants remove the exposed materials, and remaining the photoresist protects the for unexposed area. And then the later the photoresist strips is being etched out of the wafer. So this is the whole etching process. And now I will go with the what is the wet etching and dry etching. There are the two etching process. So in wet etching, as we can understand, the wet etching itself is like we are just going to use some of the liquids, like that could be in chemical in such a way as acid, base, or multiple liquids. So like example like HF, then SiO2, KOH, TMAH, like there are the multiple chemical names for silicons itself. So we are going to use it. Reason what is the wet etching is doing, like it is isotropic, like when this is a wafer and we want to remove the certain portion. So isotropic means it will be reacted in all the directions. As you can see in this image, for the second types of etching, you can see the first image. In that you can see the isotropic s, that the upper portions are the devices, and the lower portion we are going to remove the certain portions. So with the help of the wet etching, we are going to remove the all over the surrounding. And the dry etching is like anisotropic etching basically. Anisotropic etching is like vertical, sharp, or clean edges. Is while we are supposed to require a certain amount of edge, we are as precisely and considering. So you can see in the second image and the third image, right? There is a directional etching. Like we are having a desired etching process. So in that, we are going to use the dry etching. And in the vertical etching also, there is already desired. So depending upon the requirement, we are going to do the etching process individually. And this is done with the different types of processes, like RIE, reactive ion etching, ion beam etching, deep RIE. Eventually, wet etching is also done with the multiple steps. And advantages basically of dry and wet. For dry exam advantages, it is simple setup. So you can just form the simple setup, and it is not just complex structure you need to purchase, eventually not a low expensive structure. So dry etching, wet etching is simple, highly sensitive, selective, and low cost. And whereas this whereas this dry etching is basically precise for for patterning and ideal for sub micro features. And no doubt it's higher in cost and more complex structure. But yes, depending upon the requirement, we are going to do that. And yes, this like why we are basically using this because of the selectivity to the mediums, like from high to low, depending upon the we can say it as like a requirement, then other multiple parameters.
Okay, now I'll continue with the diffusion. Now I'll explain the diffusion is with the very basic. Diffusion is uh, diffusing, like putting something in a area, and then it would spread it out in on its basic phenomena. Now diffusion is the process of introducing dopant atoms into the silicon wafer by thermal activation. We need a thermal activation because with the annealing part it could get very easy to do the diffusion. Now process flow, we'll have some sort of solid gas or liquid. It would be diffused inside based on how we need. As I shown a oxidation furnace or a thermal furnace in the oxidation part, we can use the same furnace if we want. We just need to change the bubbler. In bubbler we need to add the material which we want to do. Material can be n type or p type depending on our requirement. In those n type, p type can be boron, phosphorus, arsenide, bismuth, based on what we need to do. Now high temperature annealing, after first of all diffusion, I'll explain diffusion with the first of all we diffuse it. If we diffuse the atoms, we need to spread it and make it working. Like for to diffuse it, we'll diffuse those atoms in drain and source. It would make a proper tub like shape, and those atom would be set out there in n type or p type, and we'll spread it out with the annealing. And annealing must be at 800 to 1100 degrees Celsius to make sure those dopant atoms should be diffused in a silicon lattice. And we can it is much so much control that we can have a desired depth and a concentration in a diffusion. The more the concentration can with the more it would have more mobility, and we need to measure the understand the how much doping we need in source and in drain to have a proper transistor to run. Like if source have more and drain have less, then there could be a uh, like a difference in I would say that VTH. So there would be depending on the concentration, VTH can also change. Now diffusion, as I said, P type and N type, we need to dope in source, drain and base regions. Now key parameters and time and temperature. More the temperature, more the diffusion, more the time, more the diffusion, more the depth. Here for diffusion we need to understand the fixed laws. Fixed law, there are two fixed laws, one for the diffusion of the atoms and second of the spreading out of the diffused atoms. And there is also a continuity law. It is almost same for the like how the atoms are diffused in it. So we'll surely make a next webinar we'll understand the fixed laws in a deep manner. Now if we have diffusion, there is also sub similar part, ion implantation. There are different we can diffuse atoms in two ways, diffusion and ion implantation. Now ion implantation is almost similar than this, but ion implantation is more precise. It is used in more deep submicron technology, and it is very like precise and have a controlled more control than diffusion. So as I said, the we can use the same furnace. We need just to change the bubbler on the diffusion furnace diagram. If you see impurity in solid form, this is a bubbler, as we have seen the oxidation part. So it is made up of the whole furnace is made up of quartz material. Just to have a better temperature, so quartz does not melt easily. So we use quartz material furnace. and then ion implantation. As I said, diffusion and ion implantation are similar to like for doping, it is almost similar, but have a different technique of doping. Now, ion implantation, we need ion sources. It would accelerate with the magnetic power and an accelerator, and then with the some sort of speed and some sort of power energy, it would be targeted at some specific area, and the atoms would make a trench isolation in it and form a proper trench, and those dopant atoms will be make some space, and after annealing it would form a proper doping inside the drain and source. So it is also, as I said, it is expensive, it can damage the wafer, but it is better for the submicrons, and it is a guaranteed better technology for diffusion, and it is very controlled if you use it precisely. And as I see it, same for the diffusion, we need to do the on source, drain, and a base layer. So ion implantation have its some issues, but it is very amazing, like very beneficial for use. As I said, achieve precise dopant concentration, we can have a proper precise depth control and a proper control over it. It makes trenches like junctions in it, offers better uniformity, compatible with lower thermal budget. So this is a general diagram. I have a ion source over here. It would go, it makes iron, and it would get the magnetic quadruple magnetic. Like if we understand basic magnetism, the magnetism would be formed like this, and there circular path, and someone similar like, and it would accelerate it fastly, and with those magnetic coils it would make a like very shallow trench path, and it would moves accelerated and shoot into the silicon where we want to make a where we want to diffuse those atom inside the silicon. It would make a trench and depth, and then we would anneal it at 800 to 1100 degrees Celsius to make a proper doping inside it. And then we come to the deposition. Now deposition will be explained by Jayshree.
So basically, what is deposition? Basically, deposition is like depositing something. Then, depending upon what is depositing, so we are creating them. I mean, devices like multiple devices to add upon the layers. Basically, deposition is a process of adding multiple layers, thinning the layers of like metals, like insulators, semiconductors, depending upon the wafer of the silicons and requirements. Basically, so, and what is deposition? There are two types of the deposition. Like we can do is like in fabrication, like aluminum for interconnects and copper for dimensions processed and titanium tungsten for the barrier layers. Different types of the depositions have been made, and basically what are the key factors. So what we are supposed to keep in our mind while depositing any of the, I mean, metals, non-met, I mean, insulators or semiconductors, like film uniformity. Like if this is the wafer, if this is a wafer, like only certain materials is being deposited here and the rest of the is being not deposited, and it's like idle. So yes, this wafer wouldn't be used further. We are supposed to make sure that the whole wafer is getting being deposited and exposed over the deposition layer. Then the addition and the stress, how much amount of we are giving the, I mean, addition process. Like addition is like, we can in the simple terms we can see it as like gum. Okay, we are going to stick it. Like, in that way we can understand the addition. And the stress is the amount of the like it is going to sustain the like pressure, environmental stress, multiple parameters. And like for this, there are three parameters which are used in the deposition, like it's PVD, CVD, and ALD. Basically, what is PVD? It's physical vapor deposition. Like physically, we are going to deposit, and we are not going to change the chemical components over it. Like materials are being evaporated and then I mean, either sputtered or due to any of the thermal gases, or then it's being sputtered on the surface. Now, consider a source and the target. What is source and what is target? Substrate and the target. Sorry, substrate is like what we are going to deposit, and target is on what we are going to deposit. Think in that way. And this in this image, you can see this image is basically of the sputtering. So there are two types of the PVD techniques, that's sputtering, and one of the other is thermal evaporation. So basically, firstly, we will go for the sputtering. So in this image itself, you can see there is one argon gas, then we are providing a current. So what is basically sputtering? Sputtering in this, we can use it in this way. Like we are going to heat up, we are going to provide the argon gas, and then we are after giving the current, this argon gas is going to react with the substrate. So that will create the I mean, a blue light structure, which will be plasma. And plasma is like it's multiple numbers of ions, like multiple. There are number of ions over there, and bombarding that's like plasma is getting actually generated in the vacuum itself. And then plasma, it's like only the desired materials or the ions are getting to the target, which have been which are supposed to deposit it, and the target is being rotated. And there are the two sputtering techniques. One is the RF sputtering, and another is the DC sputtering. Both are having their own advantages over each other. And RF is like radio wave frequency current, and radio wave, and DC is obviously we know that direct current. So yes, basically, what is the sputtering process? So first of all, we will generate the plasma in the vacuum, and then argon gas is injected, and then the target atoms are disclosed and ejected. Then atoms condense over the wafer and form a thin light structure over there. So this is the and the what is the thermal evaporation by then? So it's like heating the metals, evaporates into the metals in the vacuum. So there is a one vacuum and there is the metals. So that is going to heat up, and the vapor travels in the straight line and condenses on the wafer itself. So it's like good and simple eventually, and it's a basically uniform coated structure. The most important and the limitation of the thermal evaporation is like the coverage and the complexity is too much. So instead of thermal, we are going mostly using sputtering techniques. And then reason is uh, main advantages of PVD is like it's clean, controlled, and deposition rate is also controlled. So basically, it's like suitable for the back end, good for the conducting films like metals. And the disadvantages of PVD technique, physical vapor deposition technique, is like it creates trenches on vias, and need of vacuum and precise control system. And this is the main disadvantages over it. There are multiple applications of the PVD and CVD over it. Now CVD is like this is
So CVD, chemical vapor deposition, as she said, in PVD there are few limitations that are covered by the CVD. On in the figure, if you see, there are a few substrate we can there are few target we can put it. Target where there are wafers are put, and in case of substrate, we just change it with the gases. There are several different gases that gases pump which could be connected with the over there, and with those gases are then comes into the vacuum chamber, and those vacuum changer those gases are thinly very small atoms are gone through those chambers and will be deposited in it. There are several types of CVDs. Like there are more than 15 or 20 types of CVDs. Can't name all of them, but LP CVD, PE CVD, MO CVD, ICP CVD, there are thermal CVDs, there are ceramic CVDs. So there are several CVDs have different applications. Generally, what industry uses LP CVD, PE CVD, and MO CVD in most of the cases. Other than that, if there are high advanced applications, they use different CVDs. Now, in case of PVD and CVD, PVD they use substrate as a some kind of chuck or metal. In the chemical, we just go from like chuck to a proper chemical material. It is a very uniform. It has a better step coverage. It can we need a vacuum of a very high 10 is to minus 6 to 10 is to minus 8 torr, but it has a real high temperature, and it can be used to make a thin films of oxide, nitrates, polysilicon's. We can make a quantum well structures. We can work on micro LEDs, many things. There are different devices we can make. Even Jayshree have made a memory store on PVD. I have worked on LPCVD for to make a passivation layer of nitride on silicon for solar cells. So there are different uses of deposition, and then there come ALD, atomic layer deposition. This is a very advanced topic of a deposition. Even it has many uses of it. We can make 3D structure, high dielectric materials, oxide, advanced node. We can work on advanced nodes. Possibly we can make every sort of structures we want: quantum, thermoelectric, optical, LEDs, lasers, VCPEL, and different whatever we need in it, materials we can fabricate on it, make a deposition thin layer on it. It is basically deposited one atomic layer at a time, like small atoms. If you see in a figure, there are atoms differently generated, and then they are deposited on it, making a small pieces out of it. And it has a precise thick node uh, controlled manner. Like it must be in situ monitoring or a read control monitoring, which is very beneficial to control the thickness of the target of the material which is to be deposited on the target. So there are different there is only one sort of thing, one ALD only. There are no subtypes of it, but it can be work in different for thin films, and it is one of the advanced depositing machineries. And metallization. So metallization is probably the last process of the fabrication. Metallization is used to make a context vias trenches on the IC. If we have we done all the processes, like we have made a source, we have made drain. So now if we want to characterize it, if we want to check it, so what do we do? What we have to do? We have to make some context. We have to have some metal layers to, if we give a voltage or a current to it, so we need a data from it. So we need to do a metallization. We need to make context to drain and source. So that's why we do metallization. It is a process of depositing metal layers. Now again, it is written a depositing. So deposition like PVD and CVD are used to depositing these metal layers to create electrical connection between different component in IC: transistor, resistor, capacitor. Now there is a small concept in it: Damascene process. Generally, if you someone who knows who have deposited copper in a transistor, they have to go through a Damascene process. The reason of doing Damascene process is, when we deposit copper in source or drain, it generally melts out and deposited very deep, and it can tunnel through the device, or it can destroy the device. So we have to make it from the scratch. So to deposit copper, we have to first make a barrier layer on it, on the source, on the drain, as well as on gate. Because if we don't make the barrier layer, it would deposit it inside the MOSFET, it would destroy it. So for that barrier layer, we use either tantalum, titanium, molybdenum, whichever we can make on it. And right now most industry don't use the copper, but if someone has to work on copper, they have to go through a Damascene process. Even for the aluminum, I have also written the tungsten, titanium, tantalum, which are used to make a proper barrier on it. So there are different purposes: form interconnects between devices, make power ground and IOPED, multiple layering wires. Now metal deposition like via PVD or CVD can happen. Patterning of photolithography plus etching defines wire shaping. So there are different barrier addition also has to be done. Like as I said, after making a barriers on a to deposit copper, we have to also planarize also to it. If we otherwise there would be no uniformity to it. So we also have to do the chemical mechanical polishing. So generally, to make a metallization, to do the metallization, we have to go through PVD process. And so if you see in this figure, this is how a fabrication has to be done. After fabrication, this is a source on the left, this is on the right, this is drain. And after making a metal contacts, we have to do there is this oxide layer of CVD oxide to make a passivation, and another layer to make a oxide layer of a barrier, and another layer of the layer to make a passivated coming through the other different types of materials as a contamination. So in this process, I have explained the damascene process. As I said, we have to make a barriers, then we have to deposit in it as deposition barrier. Now electroplating. So these are some of the ideas of how to do the metallization for different materials. Now characterization, Jayshree will explain the character.
So basically, what is characterization? Characterization, the word in this semiconductor domain, says like we are going to characterize like the device which we have created is actually defect free to measure and analyze its physical, chemical, electrical, structural properties. So the reason why we are going to do is like to check the material quality, thickness, layer, and the doping level. So the amount of the thickness which we have been created, then the material quality, like if some of the time, if the process, I mean, if any of the side of the wafer is been getting defective, so how would we getting to know? That is with the help of the characterization. Then to check the contaminations present over there and the process deviations, and eventually check its the electrical connections, electrical behavior to check its threshold voltage. Then if there is some amount of the leakage current present over there, then to check the leakage. This is the most important step after fabricating a device, because before getting into the market, a device must be checked, and that is done with the help of the characterization itself. So there are the multiple ways how we are going to check the, I mean, characterization. So firstly, we will go with the physical and the structural characterization, as this image is having so many of the terms which might be not, I mean, able to understand. So firstly we will go with the ellipsometry. So for what the tools are being going to use is like optical ellipsometry. Why we are going to use it? The reason is to measure the film thickness and the reactive index of the wafer which has been fabricated. Then SEM and TEM. What is SEM and TEM? Basically, it's scanning electron microscope and transmitting a transmission electron microscope. So why we are going to do this? So, and even the tools are actually itself named as SEM and TEM. The reason is to check the higher resolution of the image and the cross section of the fabricated device to get the perfect actual image. I mean the connection. I mean the crystallography among the wafer into orientations, and everything is being captured into cement surface. And then TEM. So TEM is basically checking the atomic level internal structures. Then AFM. What is AFM? Atomic force microscopy. Basically, its device is also known as AFM. Why we are going to use this is to check the surface roughness and topography. The amount of the roughness which we have been created while depositing the layers, we need to check over it, and if something is being required, then we are again going with the cleaning process, like cleaning then polishing process again and again until we get the perfect roughness surface is removed. Then XRD and XPS. XRD is X-ray diffraction, and XPS is X-ray photoelectron spectrography. So to analyze the crystal structure and phase analysis, and eventually the composition bonding eventually of the elements which have been used, which has been formed into the wafer. So then what are the electrical parameters and how we are going to check its electrical characteristics? So one of them is like CV characteristics, IV characteristics, Hall effect, and four probe method. So basically why we are going to do it individually is four probe is like to measure the sheet resistance of the film. Like if there is how much amount of the sheet resistance of the thin film is able to do it, we are going to check it, because while forming an I mean device over it, it's difficult to create what amount of the resistivity it should be having. We are going to check with the four proof method. Then CV and IV. Basically, it is able to extract the oxide thickness and doping profile in CV, and IV is the current voltage characteristics of MOSFET, diodes, and transistors, multiple amounts of transistors. And what is the Hall effect? Basically, it's like to check the carrier concentration, the type of N type, P type, mobility, everything is going to check in Hall effect. Then chemical compositions. Basically, it is going to be characterized with the help of SIMS, and FTIR, auger electrons, and EDX. Basically, what is SIMS? It is secondary ion mass spectrography. Basically, what is purpose of doing this is to check the dopant profiles and the depth. What is FTIR? Basically, it's Fourier transfer infrared spectrography. It's basically defines like bond types in the film. Thin film, what are the bond structures created after the deposition of the layers, eventually before? Both are going to be checked with FTIR. Then auger electrons, like surface and elementary analysis. It is basically attached with the SEM. As we got to know about the SEM, scanning electron microscope. So auger electrons basically they are going to receive the data which have been like it's the data we are going to get about the structured wafer. And the reason why the characteristic is critical. Basically, it confirms each of the steps, and it's done successfully or not, helps to debug the failure, and then to meet the required parameters which are required by the manufacturer person who is doing the theoretical knowledge. And for everything, it's basically much more required desired partners, I mean desired thickness. So this characterization is a critical process, and after each process, where characterization is done, actually it is done by individual steps. Basically, after oxidation, then etching, implantation, deposition. Almost every time we are going to do this characterization process, and eventually before the final packaging. And these are the same and tem images, as you can see. This is the device specifically, and here is being the wafer kept over both of the sides, scanning electron microscope and TEM also. Then there is a electron gun spreading the electrons, and we are able to find the image of the SEM and TEM. Then we are going with the dicing. What is basically dicing? So what is dicing? I mean, the word itself term is like dice, like cutting of the wafers. Then wafer or die or a chip, whatever the terms we are using into the market. So basically, when we are going to use this dicing, either while we before packaging or after packaging. There are some of the basic, I mean, multiple requirements according to which we are going to do the dicing. So, what is dicing and what is the process of the wafer? I mean, dicing process. So, firstly, we are going to mount the wafer, and we are going to this is some of the layer. We are going to mount a wafer. So, we are going to stress over the metal frame. This setup establishes the wafer during cutting. Okay, so then we are going to set the alignment, like optical system which are going to align the script lines, which are non-functional gaps between the ICs, and it's making sure that we are before while cutting, we are not just going to remove the device itself. So there are the cutting dicing, which are the three types of like diamond cutter, laser cutter, silk dicing, eventually much more, which can be I will be showing to the next slide. So we are going to pick the die in a very, pick the die in the vacuum and automated handler, so that the individual die from the tapes, and then these dies are the ready for the final testing and packaging. Okay, so there are different types how we are going to cut a wafer. So basically, blade dicing. Blade dicing, then silk dicing, and reason is like why we are going to do the dicing. Basically, there are I will just help you with the blade dicing, laser dicing, plasma dicing, mechanical sawing, silk dicing, and scribbling. So the most widely used is blade dicing. Blade dicing is basically done where like during the industrial, like as you can see in this image, this is the blade diagram. So there is the wafer itself, and we are going to remove its individual wafer. It's being cutted with the help of the blades, and then laser dicing. So what is basically laser? It's a, like we can say it as a laser light, and then it's on the markings. Make sure that there are the markings and that are clearly visible, because if the markings are not the clearly visible, then we are not able to do the dicing properly. Either we are going to cut the device which we have been created, and multiple things can be happen. So yes, markings are much more required. That has been created while masking itself, while creating the mask, and while masking, this has been created the markings. Then laser we can term as a laser light, and we are just providing a laser, and this, with the help of that, we are able to dice the individual dice. And then plasma, like what is a plasma? As this you can see in this third image, there is a plasma generated, right? So what is plasma doing? So plasma dicing is actually into the research topic, not yet into the domain or industry purpose or research. It's still in the research. No one is using basically, but exactly we are going to focus the plasma into a certain linings and markings, and then we are going to cut it. Then what is scribbling and breaking? So as we know that, like during our childhood times, we are just going to adjust the marking with our nails, like on a paper we are markings with our nails. So while marking with our nails and then just removing the page outside, so that, yes, exactly same is the scribbling and breaking. We are scribbling with our hand and removing with the help of the breaking it. Okay. So still the dicing, it's again a laser based technique, where we are within the wafer, which is actually able to remove the with the splitted area. And mechanical sawing, as the word mechanical sawing itself says that, like it's mechanically cutting the, like there is not just a mechanical, this is just an example which have been showed in the image. There are the mechanical cutters which, if the wafer is too small and then we are just able not able going to use this whole process, then there are the mechanical I am not sure about it, but yes, there are mechanical instrument where how we are going to scribble it, and we are going to cut the wafers into dices. This was about the dicing, and I think we have done with the presentation. Actually, I would like to go with any of the questions over them, or
Yes, first of all, I would like to thank Bhavesh and Jayshree. You spent your time today with our audience. And one more thing here, to the audience, I would like to say this webinar is not will just vanish. It will stay in our channel. Right now, who are watching, they will live. Later, they can watch it as replay. So this is the difference with the very common format of the webinar. That's why we are started this webinar, because many times people, due to the office hours or personal necessity, they miss the timings. Even that happens with me also. So the semiconductor webinar, this will be archived and people can later watch and replay of this entire episode. And now we'll move over to the question. Before that, I would like to emphasize one point. During the, I think, etching and that part, I think Bhavesh or Jayshree, someone was saying about multiple metal layers and all. So in our channel, I have created one video which talks about the three different sections. First is called the BOL, MEOL, and FOL.
back end of LI. Yeah.
Yeah. So these three things are actually, I have segregated in terms of the designing aspect with the fabrication aspect. So that video
Yes, sir.
connects. Yeah. So I think that will be very good. I'll mention that video link in this video description as well as in the pinned comment. And one more thing is that I come up with some of the comments here. I would like to flash. This was the very first comment. I think Shagun said, well stated. I think it should be well started. I think that time we had just started and within 5 minutes it came. So thanks to Shagun for appreciating effort of our presenters today. And now I will go to another comment here. So here I think KL Sony or KI Sony, I cannot actually differentiate. So he or she might have said that very good. So that is again appreciation to uh, our presenters today, Bhavesh and Jayshree. And I'm taking their name in the alphabetical order. So please don't get offended. So, and then let me uh, I think Karthik has said that sometimes voices go suddenly. So this is a network issue, right? Because here we are using our YouTube server along with the StreamYard server. They are connected, and it's a high level networking happening. So if there is some sound is going down, it is because of the networking. So because servers are not here, servers in the US. So the transmission is coming to you through a lot of routing. So it's a physical thing, and inside our studio we did not hard any glitches. So probably it was because of the networking.
Actually, I
And
would like to add one more thing.
yeah,
Like we are, I have a whole lecture recorded this, like in,
okay,
like I have it on LinkedIn. If someone thinks like it is not properly, I have forgotten, like there is something missing or something which he or she didn't understand. I have it on LinkedIn. Go through my LinkedIn,
yeah,
Bhavesh Motwani, you will get it. The whole
yeah. Bhavesh, you
lecture.
can share me. Yeah, share me the link. I will
We'll
also
share.
mention the in the pinned comment.
Sure.
So yeah, so
And
people
we'll
whoever
soon
comes
be
here,
we both will soon be giving lectures for the VLSI for all. If they want to understand in-depth concept of the fabrication for every aspects of the fabrication, it would be like really great for them. It would be very understanding. We'll clear all the concept. Like I have gone through the Fick's law and all. Many people wouldn't have understand the Fick's law and any things, but we'll cover everything if they would love to join us.
so and one more thing, this is not the single webinar. They are you are seeing Bhavesh and Jayshree. So they have lot of slides. But however, we today kept one particular section, so viewers can expect them once again. Once again, you can expect. So probably we'll arrange another session on that. Will be different topics, and I would like to flash other questions here. I think. Mr. Dayanand Shambhu has asked that increase in clock latency impact on design. Now, I would like to draw a marking line here. First of all, there are two parts. One is the design before the GDS2. Another thing is after the GDS2. Okay. Now, once the GDS2 is ready, right, you cannot do anything. And after that, the fabrication part starts because that goes to the fabrication unit. And this question is before GDS2, means the RTL to GDS2 flow. I think Jayshree has on the fly has answered. However, this will be more if we can bring someone from the physical design part. And
Basically, we have to check for those constraint SDC file to have a proper timing closures and everything. So that's the timing closure and clock latency part. So it's as
yeah,
SDC part.
one thing can be said roughly that if there is much more latency, it will increase the clock network, right? And eventually the area will be impacted, so area will become bigger. Okay, so this will be impact on the actual silicon wafer. So in short, this can be said, but however, step by step understanding will require a lot of analysis. And I think I'll unhide this. And now again, I think Dayanand Shambhu has asked that generally how it impacts the in terms of timing by increasing the latency. Now these are the questions because one is that when we go for the final after STA, we freeze it, right, and we give the GDS2 as marked as that we are ready for tape out. So before that, all these things will be happening. And after that, today Jayshree and Bhavesh are presenting in terms of the fabrication lab. So here the designing is not in picture; it's a different domain. Obviously, you have asked question. if we have some experts in some of the webinar, we will be waiting for you to ask more and more questions. So that will be because these are highly specialized zones. So the person who is working on front end might not have the detailed overview of the back end. Even the person who is working in the front end of a custom design don't have the exact expertise of the custom of the digital design, that is RTL to GDS2 design. So front end even in two cases are different, even the back end is different. So it is a very highly specialized sector, and it's that's why it is called deep tech. That means you have to go really deep to understand the thing. So I would here I would unflash the question, and I think another question is here. Patel has asked that what is the roadmap for VLSI core semiconductor company for fresher for tier 3 college?
Well, the roadmap for, see, personally, VLSI is a different little, and semiconductor roadmap would be different. After you understand the VLSI whole roadmap, like from verification, RTL verification, PD, DFT, all these things, after getting GDS2 file, the things change in the Fab Lab, the whole Fab Lab thing. So there are two different roadmaps for VLSI and for semiconductor company. Semiconductor, as I have given today's basic for semiconductor flow, so you could understand, if you see the very first slide itself, you would understand the semiconductor flow very easily. And if still there is any problems or anything, comment right now, or you can connect us on the LinkedIn. We'll definitely share our insights with you.
And
Basically,
yeah,
okay,
and
so
yeah,
I would like to add one more thing over here. Like, think in this way: there is two backend and front end, as in IT domain, like right. So there is a backend and front end. Multiple people works on eventually front end, and multiple people works on the back end. So yes, VLSI is actually a front end in the terms of design, RTL, GDS2 file. Everything is in the front end. What we actually see. And what is the backend process is like semiconductor totally how the device is being fabricated, how we are going to in terms of the market what we are going the actual device na? That how is being fabricated is in the semiconductors. So if you are targeting any of the thing like you're just only targeting for the semiconductors, then there is a different roadmap eventually, and only VLSI, then just make sure to whatever things you are going with, like the things are you're in mind, first clear of yourself and then think of in which domain we're actually trying to go.
so one thing I would like to ask Jayshree and Bhavesh, as I have a lot of communication with you before this actual presentation. So you two guys came here. I think this guy Patel wants to know how they can approach this kind of internship or something like that. I think this is his question, but however he wrote it, it's reflecting a different meaning. So yeah, Jayshree or Bhavesh, any comments?
Okay. So yes, I would like to add over it. Like it's not like we have been on totally jumped into the semiconductors. We have a vast. Eventually, we have did the masters in this, and then we are able to come over this platform and able to make sure that yes, we are not just I mean expert. Obviously, no one is expert, but yes, a good amount of knowledge we are having. So we were into our college where we got to know about semiconductors. I will just add over here for the semiconductors, not about the VLSI. Yes, the semiconductor is actually a new trend into the market, and to be pioneer is a very important thing. And to know everything from your own experiences, then YouTube videos and searching into the web is a bit difficult. But yes, if you could survive, then yes, you are there, almost there to your targets and goal. Keep going. I would just add over it.
I'll just add
Great.
one more thing. Uh, After getting this much opportunity in Nirma, like I would thank Nirma and my faculties, because we were also like we were understanding all this through theoretical part. We understand all the theoretical part until we got a practical knowledge of going to CSR lab Siri Pilani. We did all the practicals, we saw all what is going on, and then that bridge was there which would get cleared very, like, we understood, and that what made me like, I have to get into the fabrication, I want to change things, I want to play with materials. That what changed in me. And there is also, I would add one quote. It is very a cinematic quote. If someone has seen Oppenheimer, in that guy told me only the theory will take you so far. Just to understand theory, you won't understand what is behind it. You need to do the practical side, you need to go through practical side. So yeah, even before podcast, like, me and Jayshree, we are in the same company, we have a chit chat little bit that. So we also discuss that if India wants to grow in semiconductor, what should India do? We think that someone should come with like Maven Silicon and VLSI, for all they are doing theoretical, but they are training people for the VLSI design side. But someone should start this type of like courses or some type of for the practical. Say they should start a fab lab for the students who are well capable enough. IIT have their own fab labs. There are private institutes that could afford few machines. There are many government colleges that can't afford. So someone from the government or someone from the private institute should start taking courses, should start taking lessons for a specific semiconductor, like, view a semiconductor. We can find talent. We will get a many talented people who are probably in the design side but can understand semiconductor in a brief idea. We'll get a brief idea, and we'll have a many much talented people. Like, we know the Tata have sent the many hundreds and thousands of employees for training to the PSMC in Taiwan. But what if we start training centers in India? What if we do things in India itself to grow India in the semiconductor mission? So these are our point of views. There are many things India could do for 10 to 15, 20-year roadmap is there. Like, what should India do for 10 to 15 years, and it would grow in it would help India for the semiconductor missions.
Yes, I would like to add one thing here that for generic roadmap, we have a marathon video. Actually, we created multiple Q&As. Like today, we are receiving the question online, right? Right in the live. Previous to the starting to the podcast, I have done the individual live of mine, and there I used to attend question and giving the hints and all. So what we started to did, we started to create Q&A episode that is purely non-technical. That means there is no technical thing, but non-technical, like how a person will go. So we have addressed multiple sort of questions. That is the roadmap of a fresher, and we have clubbed into a marathon. So that marathon, if you go into our channel and search it, don't worry, I'll add that link here since it has become a relevant question here. I'll add the link so that you can see what are the non-technical roadmap side that you have to cover. Okay. Now, technical side, I think Bhavesh Jayshree has given a glimpse. Another thing I would like to mention, we run the semiconductor podcast, right? Me and Munmun. So a lot of guest comes for the freshers and the experienced guys. I will request that you go and see those because we go in a very thorough questioning for the guest there, and we ask that what things are need to be done, like that. As Bhavesh said today, one of our guests said in one of the podcasts that today India has almost say 200 companies, but it will require 20,000 companies to become independent in nature. And this includes all from the design house to the fabrication house and all. And another thing, we felt a need that there is a terminology called peer learning or peer-to-peer learning. Most of the seminars and the things happen say at some hotel, and there is time gap, or you might have a work schedule, you cannot go even if you book a slot there. So that's why you get missed. So we started this semiconductor webinar so that people who are voluntarily sharing their knowledge, they can come here, and the knowledge they share will stay archived. So even if you miss the live transmission, you can later watch it. And today we are lucky to have Bhavesh and Jayshree here. And the previous episode to that, Sumanto was there on talking on the GUI of the, I think there is a analog development. So from the IIT Bombay. So and more things are coming in the semiconductor webinar. So we have bifurcated two different lines. One is the TSP, which is for the guys who have a long journey experience and they can share their journey, share their expertise view on the country's roadmap and what to do, what not to do, and lot of questions. And the peer learning, that means when you learn from your peers is the best. And today Jayshree and Bhavesh shared a lot of things which I'll encourage them. They should keep on doing that, and I will uh, ask the students to take this as an example and come forward. You can connect us with the email, that is business@techsimplifiedtv.in. If you want to come and into this particular webinar, you can also connect me on LinkedIn. So it's open. So until or unless we are sharing and opening up, the closed house events cannot actually cater our country's total population. That is a very limitation, and that's because the first reason me and Munmun started this Tech Simplified TV, so that it can reach a broader audience. The person who is seeking knowledge must get connected to the knowledge. So the knowledge is out there. So there should be a connecting tool, and YouTube was the connecting tool. So we dumped a lot of information from our experience. And today we are lucky to have Bhavesh and Jayshree here. They are sharing their experience. Today they are budding engineers, and tomorrow they will be professionals, and they will move hierarchy, and probably sometime again they will come back in their journey in the semiconductor webinar. And that should be the culture, because what happens in VLSI industry, the things continuously changing, even where the in the fabs, right, the diffraction, light diffraction technology, that also changes time to time to accommodate the lower nanometer nodes. And for that, all the things, even the lens maker has to make a lens so that it can actually beam the proper light into the onto the silicon wafer, or maybe onto some layer. So this technology in either side, either on the designing side, EDA side, or it may be in the fabrication side or post fabrication side, even in the PCB side. Now we are having multi layered PCB, means in one particular PCB you will have multiple metal layers, so through the via connects. Now these technology are changing in so much speed, you cannot get all the knowledges from the book. So please stay tuned to the semiconductor webinar, because that will help to feed your hunger for the technology. And today we are lucky to have Bhavesh, Jayshree together and presenting on this. And now I will flash the another comment. So here there is another comment from Jai Hind. I think it's nickname, and he mentioned that great. So you know personally him, right?
No, I don't know Jai Hind actually. I've heard
Okay.
first time. So
So I think some fan of you has said that great to see Mr. Bhavesh. So probably, and it's a nickname, so we cannot address him with his name. But I think people has today reacted a lot, and one thing that even people from design domain are asking question. Yes, that's good, because VLSI is all about knowing the adjacent technologies. Now, what is technology? Technology, that means, as Jayshree said, that it could be front end or back end. Even in VLSI, if I say front end or back end, the front end guy should seek for knowledge about the back end, because whatever he's doing will ultimately go to back end. And the back end guy should go and connect with the fabrication guys, because whatever he is or she is doing in the back end will end up in the silicon plate. Okay, so the technology connectivity, or the adjacent technology connectivity, and the technology exchange should be there. And it's a very difficult process. No book cannot accommodate it, because until that by the time you publish a book, right, the technology has become old and the new technology has come. So it's very rapid change. And for that, I think the webinar thing is very good. Or in future, if some other new technology comes, which is, I think, only come in our imagination, and imagination can become true, so that will help. So from my side and from audience side, I would like to thank Bhavesh and Jayshree today for presenting on in the detail and industrial perspective. And yes, the entire presentation was very, very different from whatever we read in textbook, in terms of a lot of infographics was there, and lot of explaining by means very simplicity. And I would like to thank Bhavesh and Jayshree. So as I don't see any comments here, I will be closing the session. Before that, Jayshree or Bhavesh has anything to say?
Thank you very much to having us on your platform, and we loved it. We want to share the knowledge to India's semiconductor mission. We want new talents. We want everyone to grow, and we'll surely have a next session, a next webinar on some
Yes,
new topic, on a different topic, a high advanced technology, and we'll surely meet.
yes, sure, sure. Probably we can schedule that for next month. So, uh, sure, sure.
Okay,
Uh,
so thank you from my end also. Like, thank you for providing such a platform to explore our eventually confidence to like, yes, we are able to deliver. That's most important, because delivering is also a hard thing, because none of us like is able to deliver. I mean, from 10 only 2 to 3 are able to deliver. Thank you for providing that platform and giving us confidence that yes, we can deliver our sessions, whatever knowledge we are having. Thank you for this, and we would like to add more content. I mean, contents over this after this webinar also. So
yes,
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 waiting for the next sessions and more questions from fabrication, designing, and eventually by then we will be able to cover one of the new topics, that's packaging also. Just
sure,
a
sure.
hint,
You're
like
welcome.
if just a hint, those who are just curious and going to watch this, like they could opt for the packaging, and then we are trying, like if time permits, let's see for the next.
Yeah, it's a endless possibility. So the semiconductor webinar is a open platform, and we send open invitations for the semiconductor podcast also now. And after making couple of episodes, after beaming couple of episodes, not making, we will also keep a open invite, and so people can come and share. Those who want to share, they has to have a platform. And now building the platform took us for 5 years, and now this platform is viewed by 90 countries. Our 10% views comes from the US, even from California, I say. So
Great.
we have a huge audience and niche audience, obviously niche audience, because at least these people are not binge watchers of some OTT platform. They are highly niche, highly talented people, and across the globe we have. And uh, even through the blog, many people come to our channel, and semiconductor podcast has become popular, and hopefully the semiconductor webinar will get the same popularity from the students, by the students. And it could be even for if some semiconductor professional is there, from the professional to the professional, means it's an open platform. Come and share, and that will be the that should be the attitude, because this is a fast changing technology, and everything. And if you are waiting it to go to into a book, right? So there will be a latency, and that latency might introduce new technology also, even when you are reading the book. So things should be fast paced, and in this fast paced world, um, I think the technology should be helping technology, like we are using a technology to help technology, right? I think the word is becoming confusing, but technology is helping technology to grow the technology. It sounded a bit odd, but if you think deeply, it's correct.
Yeah, it's true, true.
Yeah. So thank you everyone for attending. I think constant viewership we are having in the live, I can see in our internal matrix. And thank you very much. And those who are watching it later, they will also get benefited. Thank you, Jayshree, and thank you, Bhavesh. We'll end our stream. I think there is one more question here before we end up. So I'll flash the question. Is it okay to join IIT Bombay VLSI at age 25?
It is
Okay.
always okay to switch jobs. It is always okay to do new things. It is always okay to start new things. Just join it, learn it, explore things, and try out different things. If you would love something, stick to it, advance in it, learn things, explore things, and also share with others. because sharing the knowledge would also gain you more knowledge.
Great, because only shackle you have is a mental shackle. In real world, if you want to move, if you want to go anywhere by any means, there is no one stopping you. You just go ahead and explore the opportunities. Yes, that's all. I'll unflash it, and there is one more comment. By the time we are talking, I think Ashok Motwani said, "Great achievement." Uh,
My father, actually, I sent it to my father, and he's right now proud of me because I have been to probably I never wanted to study. I somehow got through the 12th and have somehow gone through the bachelor's, and now he sees me. I'm getting a great CGPAs. I'm doing all these webinars, all this podcast. So he's proud of me, and still I
so
want to make
from
sure
my
I
side,
do.
I pay respect to him also. Thank you for watching, and obviously it's good to see when
But
I am giving
it
this.
is a long road ahead. I'll also make sure I'll do something different to make sure I'll also make my other people proud and show love to them.
Great. It's good to see because unfortunately I lost my father in 2017. My mother is with here, and my I lost my father, who was my inspiration throughout my life. He was my mentor also. Uh, so I can feel it from deep of my heart when a father seeing his son there. How does it feel? Because I feel the void, so I can feel the fullness of heart. So there. So uh, yeah, it's great. So I'll unflash it, and there is another comment again. Uh, okay, so this is, I think it's a college level question. How to score good CGPA in college? So this is I think college question.
I would
Well,
just like to add over because I'm just excited to answer this. Yes, you are going to the college. Just make sure that you have the technical knowledge. If your CGP are good, bad, doesn't matter. But yes, your skills matter. And yes, there are few companies, there are few platforms. I mean, industrial level platforms. They require. I would. This is genuine advice. I mean, some would be telling like it's not necessary, but yes, to get into that place you required 7 CGPA, maximum 7 CGPA to attend it because there are some industries that they are just eventually sorting off the peoples before itself. If there is no 7 CGPA, remove it. If there is 7 CGPA up and like more about it, they will just sort you. It's just a basic target level 7 to 7.5 CGPA. That's the target, and this all is about your skills.
I'll just add one more thing to it. I don't want to brag it, but I somehow get into top five, top three somehow. I don't know how, but I'll just add I have used Chat GPT for every single thing. I have learned so much. I even ask how to make things from Chat GPT. I even learned software from Chat GPT. It shows me step by step things. I use AI for many things. Use AI. Learn for your benefit. I know how to use AI. I make prompts like very brief to make sure that he makes me understand something that I don't know. Second thing, get into some great colleges, great universities. You will score CGPA at between 7 to 8. Specifically, go through softwares, go through different EDA tools, learn those EDA tools, go through those in depth. Because during I got into Nirma, I have probably crashed like gone through all the softwares. So I'll give you, this is the best advice, because if you know the software, you know how to run it, how to use it very well, you will be already ahead of the class. And then you will know if you get into the corporate, it won't be very hard for you to settle in. It would be very easy for you. You know already the software, you know how to use it, and it would be great.
Yeah, thanks, Bhavesh, for the answer. And I'll disappear this. And there is another more comment. Meanwhile, you are expressing your thoughts. This is, let me show. This is Pratham Sharma. So I think great session with Bhavesh and Jayshree.
He's
Uh,
our batchmate only, and he
great,
also works
great,
with us.
great. So I'll disappear, and there is another more comment. I will flash it.
Fine,
So
he's
he
very.
has well said. So I think probably it is your response towards the CGPA. I think yeah. So I'll unflash it again, and I think we'll close the session today. We had a lot of interaction, technical side, and then we have gone. I think 1 hour 35 minutes we are running live. So I will go and end this stream. Thank you, viewers, for joining us today on the semiconductor webinar, and expect more and more episode on this open platform where we are promoting the peer-to-peer learning, that is a peer learning, so that you can have quick and fast knowledge about the fast changing world of technology through technology itself. So bye audience.
Bye, everyone.
So I'll end the stream now.